going to find a linear approximation to this function here. And a linear approximation is just a tangent line. And maybe you recall this point slope form of a line, where x1, y1 is a point on that line, and m is the slope of that line. Well, in this section, we're going to call the x value of this point a. We're going to call the y value of this point f of a. And we're going to call the slope of this line at that x value f prime of a. Now adding f of a to both sides of this equation, and instead of just calling this a tangent line, we're going to call it a linearization now. So I'm going to replace this y with an L of x. And this here is the formula for linearization that you should see in your textbook. In our problem, we're given an a value of 2. Then to find this linearization, we're going to need to find f of 2, that's f of a. And that just means replacing this x with a 2. I'm getting 11 minus 8, which is 3. So we found that f of 2 is 3. Last, to find this linearization, we need f prime of a, which in this case is going to be f prime of 2. But first, we have to find f prime of x. So we're going to take the derivative of this function up here. Derivative of 11 is 0. The derivative of negative 2x squared is negative 4x. Then what we really wanted all along was f prime of 2. That means replacing this x with a 2, which is going to give us negative 4 times 2, which is negative 8. All right, let's plug all of that information into our formula for our linearization, or our tangent line. I'm getting L of x is 3 plus negative 8 times x minus 2. Now we need to simplify that a little bit. And I have found that the linear approximation to the given function at the given point is negative 8x plus 19. And let me show you a picture of what just happened here. We were given this function here, and we just found this tangent line or linear approximation to that function. You'll notice down here that this tangent line makes contact with our function at the x value of 2, which we were given, and at a y value of 3, which we found. That was our f of 2 value. And you'll notice that this function and this tangent line are pretty close to each other whenever x is pretty close to 2. So our next step is going to be to approximate f of 2.1 using our linear approximation. So we're just going to simply plug x equals 2.1 into our linear approximation. And since a linear approximation is just a linear function, it's fairly easy to work with. I'm getting a value of 2.2. And that gives us an estimate of f of 2.1. And you might be wondering why we couldn't just plug 2.1 into the original function in the first place. Well, we certainly can, and we should to check our answer. If we plug all of this into our calculator, we get 2.18. That actual value of our function is pretty close to the approximation that we found using our tangent line. So this whole process checks out. And I guess as far as answering the question, why couldn't you have just plugged 2.1 into the original function right off the bat and never even found a linear approximation? I guess what I can say is that sometimes it's just easier to work with a linear function than it is to work with a quadratic function, or maybe a sine or a cosine function. So using a tangent line as an approximation to a function can sometimes come in handy. For the last part of this problem, we're going to compute the percent error in using this linear approximation versus the exact value of the function. And to do that, we will use the following formula. So I'll make just a little bit of room, and we can plug the approximate value that we got, that was 2.2, and the exact value of the function, which was 2.18, into our formula. And when I do that, I get 0.917% error in the approximation that we made to the actual value of 2.18. Now I feel like I should say that as x gets further and further away from our x value of 2, that the difference between our linear approximation and our actual function gets greater and greater, so that percent error would go up if I say used an x value of 2.3 or 2.5 instead of 2.1. But okay, I think that answers all of the questions for this problem. I hope that it helps you out, and I'll see you in the next calculus problem of the day.